Good morning, everybody. I will open the fire hose. I have 35 slides and 20 minutes. So, well, I'm just kidding here. I will touch on incremental lifecycle insurance from three angles. First, just a couple of slides on the underlying issues, then outline an approach, and then describe a workbench that we have been putting together to demonstrate the feasibility of this idea of incremental lifecycle assurance in a project that we had this last 2 years. This is a slide a number of you have seen before. The overall message of this slide is that in safety-critical systems, we are introducing problems in the early phases of development. 70% of the problems are introduced during requirements and architectural design, and 80% aren't found until post-unit testing. If you applied it in this particular context, one of the things we find is we spend 50% of our budgets currently on post-unit tests, repair work to get things qualified and certified, and that cost is growing. And we have heard earlier already that this whole business of affordability is not just facing the DoD, but the commercial world as well. In that context, and the second question is, how do we do recertification if we have a system and we make changes to it? Recertification is as expensive as certification currently, and we clearly can't afford that either, so we need to tackle that as well. What's interesting about the whole area is that these are safety-critical systems. They have pretty strong processes in place, DO 178, recommended practices like ARP 4761 and 54, and despite all of that, that community has been struggling, so that's why they were looking for a new way of doing business. And then got involved with us, the SCI, as well as the SAE AADL committee, to take this virtual system integration approach. In our particular context here for this project, we are focusing on how to leverage virtual integration around the AADL to focus on the assurance and qualification process, while in a later talk and the talk by Julian Delange, we're illustrating how virtual integration works. Just to show you how hard it is to assure that you have good quality, we will find two problems in my slide set that were introduced when I was at the last minute asked to move from a format that's a 4:3 format to a widescreen format. And you can point out to me when those two problems show up. So even slide engineering is not that easy. Okay, so we said, okay, requirement can be a problem, and I'm going to illustrate that with 2 points. One is we actually have what looks like a pretty reasonable requirement specification. And the example I'm using is actually one that Mike Whalen from the University of Minnesota has been using. He's involved with Rockwell Collins, doing also work on virtual integration and verification of systems. So when you look at this description, it looks pretty reasonable, relatively precise specification about how quickly the system is supposed to respond and everything. When you then take it and map it to a graphic depiction of the system that it's for, what we will find is that each of those 4 requirements is actually at a different level of this very simple system. So the main message is when you have a text-based representation of your system that specifies the requirements, half of the time you have architectural information in there, and the other half of the time it's not clear what the boundary of the system is that the requirements are for, and in many cases you're actually describing requirements for multiple levels of the system. Reality is actually a little worse than that. Based on some studies, what we find is when you look at the kind of requirements areas that you have, the first 3 alone are taking care of 75% of the problems, and those are incomplete, missing, and incorrect requirements. Those are relatively easy ones to find. So we want to start out easy, catch the easy ones, then go to the more complex ones, and by mapping requirements to an architecture model, whether that's now a model of the operating environment and the system you're interested in, or the first or second level of the architecture of the system, it actually very quickly gives us a chance to improve the specification of requirements. So how do we do that? About 6 years ago now, we were asked by the aviation engineering director at Amerdeck to come up with a strategy for improving the qualification of rotorcraft. They have to put their signature to indicate that these things are flight-worthy, airworthy. And they're getting more nervous because instead of exhaustive testing, they have gone to a mode of test to exhaustion. That is, you do it until money runs out, time runs out. or you need to put this thing into mission no matter what. So, like I said, and you have heard before, people are getting more and more nervous as more and more software goes into these systems. So what do we have in terms of assurance? It's sufficient evidence that a system implementation meets system requirements. We are testing against requirements, so it's important to have good requirements in order to get your tests right as well. And then the second piece is, can we do it in such a way that we have it throughout the whole life cycle, not just at the very end of the system development. So we are starting out with virtual system integration. We will elaborate the details of that later on, but the general idea is we have a formal specification of your system architecture using architecture modeling with strong semantics. We virtually integrate the system and then discover those issues that we typically discover post-unit test very early in the process based on this model-based integration. And then we complement it with two more pillars. One is focusing on requirements. How can we improve those? And focusing on collecting the evidence so that at any point in time, not just at the very end, we have a good record of all the verification activities that have been performed as evidence that the system meets its requirements and the quality requirements. And it's the outer two parts that I'm focusing on with this talk. How to achieve incremental assurance? We have three dimensions of that. The first dimension is you do it throughout the life cycle. As you move from one step in the life cycle to the next, we continually not only develop but also verify. So what that leads us to, instead of having a single V where on the left-hand side we do development and on the right-hand side we do testing, we now have our double V. We continuously do both assurance and development at the same time. And in that context is where an initiative called SABI, it's a commercial aircraft initiative. They have done work using virtual system integration to demonstrate that and have come up with some return of investment numbers where they were able to show that they can bring down their system development costs considerably by using some of this virtual integration. The second aspect of incremental is to say your system is quite large, you have plenty of requirements. How do you focus on certain things that are critical? You want to focus on those that are hard and critical first. So what you want to do is take advantage of knowledge that you get, for example, out of a architecture evaluation using, for example, ATEM, where you're setting priorities, or from your business drivers, or from work like Rolls-Royce has done, where they just use input from their developers to help them understand why they have 80% of their requirements changing coming from the development team rather than the customer. Because that data gave them insight as to what places to pay attention to because people didn't fully understand what you have. So we want to support that kind of process to help you focus on verifying those hard parts first before verifying things that we already know. And then the third piece of it is to say, can we do that one layer at a time as we have an architecture in place that is from the top level requirement to the first level design and then immediately verify that back against requirements and do that throughout the whole life cycle. The second part of it is then how do we get coverage? And we have three dimensions of coverage. The first one is to say when you have a system, here I'm depicting what a system process is in terms of a definition that Differential System Engineering Society has, which says, give them a system process, it takes input, produces output, following some behavior, maintaining some state, making use of resources, and being under some form of supervisory control. So what we need to do is make sure for all of those elements we have requirements. To make it concrete, if you're doing a situational awareness system and you're supposed to track external threats, obstacles, and terrain, and then when you come to the system specification and you only talk about two of those three in terms of requirements, you clearly have one of those missing requirements. So you want to take advantage, again, of information that you have in a model that can be processed by tools so you can make sure you have coverage of those elements. The second part is we not only need to deal with functional requirements, but non-functional ones as well. And for that, we can take advantage of what's called a utility tree that deals with various quality attributes. It's something that is well established, has been used in architecture work, and is even embedded in some standards, where it outlines the different kinds of system concerns that you're interested in, and it also helps you drive them down to be concrete enough so they become verifiable. Because saying a system needs to be responsive doesn't mean very much. You need to say, what do you mean with responsiveness, and that kind of thing. Then the third aspect, since we are dealing with safety critical system, has to do now, how well does the system deal with exceptional conditions. On the safety side, they're called hazard. On the security side, they're called vulnerabilities. And again, we can use a systematic way of doing that. On the right-hand side, I have a system description as a feedback loop. And actually, it's just Nancy Levison at MIT uses a very similar picture to deal with hazard analysis on that front. And then we take advantage of a taxonomy that we have defined as part of a fault modeling standard that goes with AADL. And it's based on research in the 90s where we have said, given a component, if it fails, the effects that it can have on others is just a limited set of effects. No matter how I fail internally, if I'm supposed to provide a service to you, I'm a GPS, for example, I can not provide the location information, that's omission. I can provide it at a time when you don't expect it, that's commission. I can provide you the wrong values, so value errors, timing errors. So there's a handful of classes that we have, and they are fully specified here. So you can use that as a checklist to say, have you considered not only the thing not working, but also the thing delivering data too early or too late? And we have plenty of examples in safety-critical systems where it was just the timing itself that caused the system to fail. Otherwise, the functionality was fully in place. And we worked with one customer where they had used a SCADE specification for their engine control system, had it fully verified functionally, but they still had a problem because of timing aspects that the model checking technique did not take into account. So given this work, lots of interest in the work. OSD, the predecessor to Dr. Bonneau, was already pretty excited about this work, and Dr. Bonneau as well. A number of research groups have been using AADL and virtual integration as a platform to do their work, both in safety and security. We are actively working with a Army program that's a technology demonstrator program, and you'll hear a little more in the later talk as well, where we are bringing that technology into a major Army program that the full program is Future Vertical Lift that will start in 2020. Right now we are working out how to use this technology in that context. I already mentioned on the commercial side, similar kind of situation. Boeing, Airbus, and Embraer and their suppliers are working together and with the FAA to apply virtual integration technology and also how to do the certification. And I mentioned the engine control system case study already. In terms of standards, we are using AADL as a standard, but also the work that has happened in this particular project is getting fed back to the standards committee. We are working on a draft specification for how to do requirement specification in the context of an architectural model. And then there is a working group at SAE that does these recommended practices. They're updating the system safety practices and are incorporating AADL and fault modeling around AADL into their specification of the latest standard. And then we also have interest from regulatory agencies that have interacted with us in various ways, picking up some of these technologies. For example, the Underwriters Laboratory has been incorporating the fault taxonomy that came out of our standard into their guidance work. Okay, the workbench itself. So doing this on paper doesn't help. You need to show that it really works. We already have a workbench in place that does all this virtual integration work. We said, well, let's leverage that for our work, and that's what I'm going to talk about right now. In order to do that, we had to come up with some notations to let you more formally express requirements. And we set that notation up so that you can bring in existing requirements organized in document structure, sections, and so on, at the same time be able to align your requirement specification with architecture models. And we distinguish between what we call stakeholder goals and system requirements, where stakeholder requirements are kind of the goals, the interest that they have. System requirements are the things that become the contract against which you verify. We have verify is a notation that lets you lay out verification plans. Those are the set of things that need to get executed in order for you to then get confidence that the requirement is met. And there is all kinds of mechanisms in place that let you do that in an incremental fashion. And then we have a notation that lets you specify, given you need to make your assurance case, what are all the parts that you're responsible for and what are all the parts that you assume have been verified separately. And once we have all of that in place, we then have a mechanism in place that lets us keep track of all the results throughout the process, not just at the end of the process, but also early in the process. When assurance case work started out, they only considered positive evidence because it was only the stuff that you deliver at the end to get certified. But if you're in the middle of it, you also want to know what doesn't pass, what fails, and in what cases the test failed to run even. That's different from a test coming back with a negative result. So you want to keep track of all of those things such that at any point during the development process, you know where you have potential problem areas and can focus on those. How does some of that look like? We actually used some real examples. One of them is a multi-tier aircraft model that we had out of this SAVI initiative. You have a model of the aircraft as a whole, of your IMA subsystem and then with the various parts. And alongside the model at each of those layers, you have a set of requirements for each of those and verification plans against those requirements. And then you configure that saying, I am going to verify the aircraft focusing on my IMA or the aircraft as a whole. And that becomes then the context in which we perform our automated verification. It is a real workbench. Here's a screenshot of that. On the top part, you see a specification of how we configure our assurance case. We are saying, I'm going to verify a particular system, in this case, the whole aircraft system, using two different types of models, and we are specifying what we are responsible for verifying and what subsystems we are delegating to have been verified separately. It is then automatically run, and then we report out results. And what you get is a detailed result of all the things passing and failing, the type of failures if you have different kinds, and then we also have a graphical depiction to help you drill down where are your problem areas. Because if you run 800 tests and 50 fail, is it evenly distributed, or are those 50 failures primarily in one or two subsystems? Because again, this helps you figure out where hotspots are. So as part of the process, we support what we call user-guided filtered views to help support this one form of incrementality where you're saying, I am currently interested in the interplay between safety and performance, or the interplay between safety and security. Then in this context, the system only runs those verification activities that relate to that. And again, you also saw that you can configure how deep down we will verify at that point. We also have built in some measures that let you talk about the coverage, like I illustrated earlier, and about the verification results, like you saw on the last slide. And you have weighting factors on there, so you can kind of give weighting indicators like degrees of uncertainty that you had in different systems that you need to pay more attention to. And working with somebody from our measurement group, we then took some of those measures, mapped them into COCOMO to come up with a cost-based guidance to say, okay, this is what you want to focus on such that you can reduce the cost in your system and the effort that is necessary to maintain the system as a whole. We did it for several case studies. One is the multi-tier aircraft that you saw already. Second one is the stepper motor that I mentioned earlier, where the company had done a full verification but still had problems, and that's where we went in and identified actually two sources of timing-related errors in that system. And then the third one is the situational awareness system that we did for this joint multi-role program. In that case, we were given requirements documents, and we were able to illustrate that with that, we were not only able to identify problems in the requirements, but whatever little or much information about the architecture was in there, we were able to also identify potential system integration issues that they would run into later on by just the information that we found in requirement documentation. So in closing, what we have is the benefits for virtual system integration and incremental lifecycle assurance is on one hand, cost reduction by doing early discovery. We reduced the amount of leakage we have to later phases, and by keeping track of all the evidence throughout the whole process, making sure everything has been consistent when you start out early and push it through, we increase the confidence in our system. And with that, I have a couple of seconds to get you to ask questions.